Welcome to the Clear to Send podcast, a podcast about wireless engineering, where we educate you on Wi-Fi technology, talk about design tips, troubleshooting, interviews, and the tools. Here are your hosts, Roel and Francois.
Hello, everyone. Welcome to the Clear to Send podcast. This is Francois Vergès, your host. And today we're going to do a deep dive into the different KRACK CVEs. So a couple of weeks back, we did the first episode on KRACK. It was more like a high-level overview of the situation, and we wanted to follow up today with a more technical episode. So, the best way for us engineers to protect our companies or our customers against KRACK is to understand how it works really. And in order to do so, we have a very special guest today with us, Hemant Chaskar. Hi, Hemant. How are you?
Hey, thank you for having me. Glad to be here.
No problem. It's a pleasure for us. Thanks for being with us. Why don't you present yourself to the audience and tell us, a little bit more about you, what you do, who you work for, and how you got started in wireless and security.
Yeah, great. Hello, everyone. So my name is Hemant Chaskar. I'm currently the Vice President and CISO at Mojo Networks. And I have been in this field of Wi-Fi for more than 12 years now. The way I got started was when we were building our first wireless intrusion prevention system. So that's how I got into all the nitty-gritties of wireless security. And we have come a long way since then. So I was part of that whole journey when we introduced access point solutions on top of VAPs and then cloud-based Wi-Fi. And at this, currently what I do in addition to Wi-Fi is also manage the security of our backend cloud for commercial as well as some of security sensitive organizations which have very strict security requirements on the cloud side as well. So that's what I have been doing for the last 12 years.
That's awesome. All right. And so you've been involved with the KRACK attacks. You knew. When did you learn about the whole KRACK attacks deal? Did you learn about them before us, before everyone?
Not before everyone, but before general public. And the reason being that the researchers, handle it very professionally. They just did not go out, right? They first went to US CERT. From US CERT, the information kind of went out to some of the big vendors first, the big names, right? Fortune 500 type of names. And there is an organization called ICASI. What it does is when such thing happens, it tries to create a community of vendors for incident response, like a collective incident response to these kind of events. So they put together a community, and that's the time I got involved. So probably I knew about them maybe 2 or 3 weeks before the researchers went public, and the big US CERT advisory went out even before that, but I was not privy to that at that time.
Okay, perfect. So before getting into the different CVEs and how they work, let's do a little review on. We're gonna focus on WPA2 here, so let's do a little review on how WPA2 works with you, Hemant, if you don't mind.
Yeah, I mean WPA2 is, as we know, the current encryption authentication protocol for wireless links. And what is relevant here for WPA, part of WPA2 is what we call CCMP. CCMP is actually the method that is used there for authentication and encryption of the packets, right? So these type of combination ciphers, which do both authentication and encryption, they are called AEADs, authenticated encryption with additional data. So I will explain what that means, quickly. So one part of these ciphers is that they provide authentication using some technique, and in CCMP it's called CBC Max. So that's a version of AES, but that runs in what is called cipher blockchaining mode. So when you receive a packet, the AES CBC runs on it, and it creates what is called a MIC, right? Message of integrity code. And the point of this is that it's not only the payload, but the parts of the header, also the MAC header, right, are also included in this authentication calculation, so that when the receiver receives the frame, it knows that the address that it received from is correct, right? Because nobody tampered it in the middle. That's the authentication part. And then after that MIC is calculated, the whole frame, which is the header, the payload, and the MIC, that is then encrypted using another mode of AES. AES is, as we know, the state-of-the-art encryption, right? Advanced encryption standard. And this encryption is done using what is called counter mode, CTR, right? And that's what really CCMP stands for. The first C stands for counter mode, which is indication of AES CTR being used for encryption. And then the second C means CBC, cipher block chaining. For MAC, that's the third M. So that CCM stands for. And these AEAD schemes are very popular these days. Even if you look at TLS 1.3, the only ciphers allowed there are these AEAD types. So it's very state of the art actually. And that's really the core of cryptography, right? That is used in WPA2.
Okay. And then so if we focus on the CTR, which is the one used to encrypt the data, basically, right?
Yes.
So do you want to get into the nonce number and the packet number?
Yeah, so AES CTR is interesting, right? What AES CTR, these type of ciphers are called online ciphers because, as I explain them, you will understand they bring in some efficiencies because what happens in AES CTR is you don't go and directly run your payload through AES algorithm, right? AES is an algorithm which works on 16-byte blocks at a time, about that's 128 bits. So AES takes these blocks and then scrambles them, right, using AES algorithm. But what you're doing in AES CTR is not directly taking the packet and running AES on that. What you instead do is you take a fixed block of data, right? And that's also 128 bits and or 16 bytes. And the way it is formed is the first byte of it is some flags, right? Then there are 6 bytes of it, which is the MAC address of the sender. And the next 6 bytes is what is called a packet number, right? And then the remaining are something called counters. So take these 16 bytes and then you encrypt these 16 bytes using an AES key first. So the AES scrambling is run on this block of 16 bytes. That kind of known in advance for every packet. So because like I said, it's flags, right? It's a MAC address. Then there is a packet number, which keeps increasing every packet. And then some counters. So this block is actually called AES nonce, right? And then after this block is encrypted, the output of this encryption is 16 bytes, and this is called a key stream. And this key stream is what is XORed with the payload data, right? And as you can imagine, the beauty of this is that you can do all this difficult computation of encryption, AES encryption, even when you don't know the packet data really, right? So you can actually pipeline this process because the encryption is simple XOR with the packet, and that's very efficient. The difficult part is this AES scrambling. So that's how AES CTR works, and this fixed block of data that is scrambled using a key to generate what they call a key stream that is to be XORed with the packets, right? So this fixed block of data is called nonce, and as you see how it is formed, all other fields are kinds of fixed, flags, MAC address, and then there is a counter which increments for every chunk of the packet. But the PN, the packet number part in the middle, that kind of increments by 1 for every packet, right? So that block is AES nonce.
So the packet number is really what is changing in between each key stream, right?
Yes, and packet by packet, correct. Exactly.
Okay.
And that's why it's nonce, right? Nonce means a number used once. So nonce stands for in cryptography, number used once. That's why it's called nonce. So the idea here is that once you use this nonce for one packet, right, you cannot reuse it for another packet. And that's the way we achieve that is by changing the packet number every packet.
Okay.
Yeah.
And we will see in the different CVEs that's kind of like what is being attacked, the packet number, right? And we're trying to reusing the same packet number in order to get the same key stream.
Yeah, that's really the key, right? Because if the packet number repeats in two packets, then what's going to happen is if you capture these two packets on the air, right, the encrypted packets, and just do the XOR of them, what happens is because like you said, the key stream was repeated, which was a simple XOR with the packet. When you XOR two encrypted packets, what you get is a XOR of two plain text packets, right? So if you knew one packet, or you can guess one packet what it was based on what stage of communication you are in, then you can actually read another packet. So because we have eliminated, right, the effect of key stream. So it's very important not to repeat that nonce from encryption perspective. And you mentioned, the PN is also abused for replays, meaning, and that's not really a AES CTR property, but that's like a replay protection that is built in WPA2, that you receive a packet for key, and then if you receive another packet, you will accept it only if its packet number is higher than what you received. And the idea there is that, okay, I received that packet first. If I receive it again, then that means somebody replayed it, right? You are not supposed to get two copies of the same packet at link layer, because Wi-Fi link layer does allow replay protection, correct? So it's also used for replay protection, the same packet number thing. I mean, that's not really the encryption thing, but that's really Wi-Fi thing, right?
Okay, so the packet number is also there to protect the WPA against replay attacks.
Correct.
Okay.
Important.
All right. So what about GCM? What is that?
Oh, that's very interesting. So, when KRACK came out, everybody focused, or all of us focused so much on CCMP because that's the currently used cipher in Wi-Fi, correct? So GCMP was like next stage cipher that was introduced. And the concept was that, okay, AES CTR is still same inside that. And in this case, the middle C stands for CTR in GCM, the AES CTR that we discussed for encryption.
Yeah.
But the authentication mechanism that was used in CCMP, I told you it's called AES CBC, cipher block chaining, and that's not as efficient to implement as CTR, because that is not a key stream based concept. For that, you have to actually wait for the packet to come in, then split that packet into 128-bit blocks and run AES on each of those blocks to create message integrity code. So that part started to cause a throughput bottleneck, especially as we went from 11N to 11AC to now 11AD, right, which is Wi-Fi WiGig. So the standards community already saw this increase of speeds happening significantly, and then there was a throughput limitation because of the authentication part of CCMP. So what they did was they said, okay, we will use a simpler, it's not exactly key stream, but it works similar to key stream based authentication called Galois hash mode, right, called G hash. And what G hash does is actually in CCMP, you authenticate first, generate a MIC, and then encrypt. But in GCMP, you encrypt first using AES CTR, and then you calculate this MIC on it. But that MIC computation it's not stream XOR, but it's like multiplication by a polynomial. It is much simpler to do than really run the AES. So GCMP is Again, an AEAD means authenticated encryption with additional data. So they call this additional data because the authentication also takes into account the headers, not just payload encryption. So that's the next stage. And GCMP is called high throughput AED. And that's because its performance is faster than CCMP, right? And it's online, both for authentication and encryption, meaning that's GCMP. So high throughput, and both of these are kind of FIPS approved ciphers, right? CCMP and GCMP. So they have been mathematically proven strong as long as you take care of not repeating nonce, PN, packet number.
So in GCMP, you also have packet numbers, right?
Yeah, same concept as it goes to encryption, but the authentication part now, if you repeat packet numbers in GCMP, then you can guess the key that was used for authentication. And now what you can do is, now you can tamper and inject, right? You tamper the packet or change the packet or even construct a packet. And now you know how to authenticate that, right? Generate the MIC on it, as well as you can encrypt because you have guessed the key stream. Then you can do tampered or new packet injection if you have repeated PN that you can observe in packets. So for GCMP, it's a little more dangerous because you can also inject and tamper.
Okay. All right. So we talked about CCMP, GCMP. Let's now talk about WPA2 and the different keys that are exchanged during the four-way handshake, right? So
yeah. I mean, of course, we need keys, right, to do any cryptography. So WPA2, if you look at, I mean, it has pretty big key hierarchy, but when you go down, the keys that you actually use, right, for actual encryption authentication. So there are three actually. The one is called PTK, pairwise temporal key, and they're called temporal, meaning temporary, right? They're used for short time, and then they're refreshed, or when you change association, they're regenerated. So PTK is, that's used for protection of packets or data, unicast packets of data between API and client, right? That's why it's called pairwise. It's for a pair of API and client.
And it's actually a group of keys, right? The PTK is a group of keys.
Yeah. Good point. So PTK is actually a group of keys. There are two keys in there called KEK and KCK, which are basically used for protection of some four-way handshake information. But then the last part of it, which is either 128-bit or 256-bit, depending on whether you are using AES 126 or 256. That's called transient key, TK, right? And that's what will be actually used to encrypt and authenticate each packet that AP sends to client or client sends to AP. So
unicast traffic.
Yeah, unicast traffic. And when I say unicast, that includes management as well, right? So if you're sending a management frame,
the probe requests are.
Yeah, so that's also encrypted and authenticated using PTK. Data management both. And the management part comes in when we talk about MFP, right? Management frame protection, .11w. So it's used for that too, or unicast.
Okay.
And then there's another key, GTK. Now this is interesting. So it's just one key, and it's kind of it's randomly generated by an access point, and then it's transported to client. So the purpose of this key is when AP sends broadcast or multicast data to different clients. So this is like one key that is common among all clients in BSS and AP, because it's a group, right?
Yeah.
And so AP tries to send some, video, broadcast video or something, then, or even like ARP packets, which is data, right? Broadcast ARPs or something, then it will use this GTK to again encrypt, right? Encrypt. And the third one is interesting. So it's IGTK. Now this one is not used for encryption. Now this IGTK, as its name says, I stands for integrity. So it's only used for integrity, and it only comes into play when you are using .11w or an MFP. So when an AP is sending broadcast multicast management frames, like let's say broadcast deauth, right? Deauthentication to clients, then this IGTK is used only for authentication of that. Because if you remember old days,
integrity.
Before .11w, you could just deauth any client, right, by spoofing a deauth. Now they wanted to prevent that, so it's used for that. So that just used to calculate message integrity code. So when a client receives a deauth, broadcast deauth, to make sure that it actually came from the API and not from some spoofer, right? So all these three keys, they are part of WPA2, and so that's a key stream. The key chain that you have really when you are using WPA2.
Okay, perfect. So now that we set the base, we talked about WPA2 and the encryptions. We can now start talking about the different CVEs and how they work and what part of the encryption process we're attacking. Right. So the first set of CVEs we're going to focus on will be attacking the EPOL four-way handshake. So the four-way handshake is the exchange of packets between the client and the AP. And then during this four-way handshake, we'll be distributing or generating the different keys to encrypt the data, right? So the PTK and the GTK.
Yeah, correct. So, when the client connects to AP, right, it has to first generate or obtain these keys so that and that's why we use EPOL four-way handshake, correct? Maybe it will be useful for to just go quickly over EPOL four-way handshake. Do you think so? Or everybody knows we use .1x EAP or pre-shared key password to do authentication to Wi-Fi. So what happens during that process is the client and AP prove to each other that they are legitimate parties, that they want to talk to each other, and they generate something called a master key in that process, and it's generated on both sides, never flows on the wireless, and it's called PMK. And from that PMK, then this PTK, GTK, and IGTK are derived, right? So that derivation process from PMK is what EPOL four-way handshake allows you to do, correct? So basically, it's four message transaction. Message one called M1 going from AP to client, carrying some information like one random number. Message two goes from client to AP, carrying another random number. So both the AP and client now have the same pair of random numbers that they combine with PMK, run a pseudo random function on that hashing function, and they generate PTK on their own sides independently, right? Same PTK. And then there is message 3, which goes from AP to client, which transports these group keys like we discussed, because they are generated by APs and transported to the client. And then the message 4 that goes from client to AP that confirms that it received the GTK. So that's like 4 messages, message M1, M2, M3, M4 as they call. And once this transaction is complete, the keys are installed, and then you can communicate using PTK, GTK, IGTK protection. So that's EPOL four-way handshake, and it has been there for a long time, right? In Wi-Fi.
And it's been secure so far.
Yeah, and it's interesting. It's formally proven secure. What happens is, for these kind of protocols, you can also do formal proofs of security, right? So you actually model some attacks, and mathematically, formally prove that they are secure. The man in the middle cannot do anything to them. So, and all that based on this assumption that you already talked about, that the PN is not repeated. So it has been proven formally secure by mathematicians and protocol analysts. So that's interesting too.
Yeah. So what about the crack attack attacking this forward handshake? How does it work?
Yeah, so the protocol is secure, but crack is really the implementation vulnerabilities, right? And uh, the way kind of to the three CVEs, which are 13077, 13078, and 13079, which attack ePOL four-way handshake. And the modus operandi there is that I talked about M1, M2, M3, M4. So block this message M4 going from client to AP, right? And then make AP retransmit message 3. See, what happens is if AP never received the last message of the handshake, which is M4, what it's going to do is retransmit the message 3 because it thinks that client never received M3, right? And
Yeah.
we are not talking about here MAC layer retransmits that we have in Wi-Fi, where if the packet gets erased, we don't get ACK, right? And then that's retransmit. So we are not talking of that retransmit. We are talking of application protocol level retransmit that because it's a newly generated M3, right? It's not the same frame being retransmitted with the retransmit flag 1. So what this crack attack does is blocks this M4 on the air, and we can talk about that how. And then the AP thinks that, oh, I did not receive M4, so probably client did not receive my M3. So what it does is retransmit that M3. And when that retransmitted M3 reaches the client kind of reinstalls the keys. So it installed the keys first time when you received first M3. And when it receives this retransmitted M3, see what it should have done is it should have said, hey, I already installed these keys, so I'm not going to reinstall them. Okay. The problem with reinstall is that the function that reinstalls the keys also resets the packet number, right? So the problem is not with reinstalling by itself, but the problem is the function that reinstalls also resets the packet number. So you first install on first M3 receipt, and now you reinstall on second M3 receipt. So as you can imagine, if a packet goes out right between those two, that PN is repeated because maybe you install first time you send 2 packets. Let's say PN equal to 1, PN equal to 2. Now you reinstall the key, so your packet number goes back to 1. So you again transmit next packet with 1 and 2. That's where the repeat happens. Yeah.
So what can happen in between the two key installations? So what kind of traffic can be generated or sent by the client in between the two reinstallations?
Yeah, and that's a very important point when you analyze impact, because see, the client starts off its normal communication messaging. So it could be DHCP discover, right? It could do some ARP and maybe TCP sync if it already knows IP address to connect to. So I think mostly the initial part of any
connection
transaction, and if you go into details, if you read the paper, you'll realize that AP does not talk during this time because it never completed the handshake, right? Because you block M4. So AP doesn't talk. So, client, how much it will progress in terms of transmitting packet is something debatable, because if you send DHCP discover and if you don't receive anything, you're not going to proceed further, right? So it's pretty limited in my mind, but still a crack. But it can send some packets, few. I mean, because AP doesn't talk, right? It may not be large number of packets, but
okay. And the amount of packet the client sent in between the two insertion is really what is important, because that is the only packet you will be able to decrypt, right? Or guess.
Yeah, because that's only when the packet number reuse happening. And I mean, you can repeat this process more than once. Like you block M4 first time and then it retransmits M3, and you block M4 again, right? And if you look at the current implementations, at least before they were patched, they were allowing 19 retransmit. So you could repeat this process 20 times for each connection start. But again, the point is, and each of those timeouts for retransmit is 1 second. So if you look at timeline, you probably had 20 seconds and like 20 iterations of this. But again, if AP doesn't talk, right? You might see repeated packets being sent, which are not useful to us, because if you sort the two repeated packets by encrypted by same key stream, you get 0. So those are not useful. So really interesting too. So it's kind of bounded by various factors, how much exposure you will have in terms of how many packets you can collect, right? So it's an interesting, clever attack, but it has some bounds in terms of how long you can proceed with this.
So in order to set up this attack against the four-way handshake, you need a man in the middle, right? You need someone in the middle intercepting the traffic and blocking message 4 coming from the AP.
Message 4 coming from the client, correct? Yes. So you have to block it, and man in the middle is one way, I would say, practical way to block it. Because if you're a man in the middle, you can manipulate, right? The package that any way you want. You can block, you can relay, you can capture everything. So that's a practical way we can. It's not impossible to build a tool that will do selective packet erasures, meaning you generate noise, right? When you see that M4 going, the challenge with that is you have to first detect that is that packet from the header, and then immediately do some noise generation. That's usually tough, right? Because you are just looking at the header. I remember I had worked on something like that, not that intense, but WIPS uses deauthentication, right, to do quarantine of bad connections. So we were experimenting if there are other ways, and we were experimenting in doing packet collision. So we detect a packet, and if that's the packet that we want to not to allow, then we will collide, transmit something to collide with acknowledgements of that packet, MAC layer acknowledgement. And that also was very tough. It was not very reliable. And in this case, it's not even ACK. It's like the later part of the packet you have to erase. So the same researcher has some papers interesting, people who are interested, and go ahead, look at his research work. So there is one paper I read there where he tried to do something like that, selective erasure, with some success, but it's not very reliable. So man in the middle is a very reliable way to do this, to block M4.
Okay, so what are the impacts of the 3 CVEs we're talking about right now? The 137.7, 137.8, and 137.79.
Yeah. So Francois, before we go there, I think it's one important thing also is that the man in the middle, right? It cannot be just any man in the middle. It needs to be a MAC spoofing AP. And the reason why that is true, because this PTK generation takes into account the MAC addresses on both sides. So you have to spoof the MAC and then get in the middle, and have client connect to you on one radio, and then use your other radio to connect to real AP, right? Like that. So that's very specific man in the middle. Yeah, impact wise, impact wise, 13077, it allows decryption prone packets from client. What I say decryption prone, because you may be able to decrypt them because they have violated the PN uniqueness, right? Assumption. It's not that you are just in clear text packets. I call them decryption prone packets from clients. And we discussed, right, there will be just few at the beginning of connection. Another thing you can do, probably don't go into details here, but when that reinstallation happens, just like PTK packet number gets reset, the GTK, IGTK packet numbers also get refreshed. And then that allows you to replay broadcast multicast data packets into the client because of the GTK abuse, that is 13078, and replay MFP, management frame protection, broadcast multicast packets into client, that's IGTK abuse, that's 13079. So this EPOL abuse allows you to do those 3 things, gather some decryption prone packets from client unicast, right? Inject broadcast multicast, not inject, replay broadcast multicast data packets into client, and replay broadcast multicast MFP packets to the client. So those three are kind of qualitative impacts of these things.
Okay. And this only happens if the client retransmit the message number 3.
AP, you mean? Yeah, AP retransmits. Yeah. So M4 going from client to AP is blocked, and then AP retransmits M3.
Okay. Yeah, AP retransmit. Okay. But some clients don't accept a retransmit version of M3.
Yeah, that's interesting, right? So researchers found out, and they call it that they didn't implement the protocol correctly. So either way they were secure already. iOS, Windows 7, Windows 10, it's described in the paper, and does not accept that. So this did not affect those devices, as the researcher pointed out there.
And if the client doesn't reinstall the key, the packet numbers don't get reset, and we're also good to go, right?
Yeah. That's finally the key, right? That's the key to the fix. That when you receive M3, what you should do on the client side is compare those keys with what you already have installed. If they are same, just don't reinstall them, send M4, and you are done, right? So if you look at the fix, is not difficult actually. I mean,
yeah,
it's very easy actually, and it's already done. The patch is available for host AP. So
yeah, so this is what the patch is all about. So if you update your client, the patch is basically gonna compare the keys and not reinstall the already in use key.
Yeah. So that's pretty easy. So then you don't reinstall, so you don't reset, and then you're going, fine.
So let's say you don't have the patch for your client. What can you do on the AP side?
Yeah, so that comes in when people usually talk about these clients, right? IoT clients and non-mainstream devices. I mean, some of them, they don't even know how to patch them. So AP side, what you can do is the message that triggers this vulnerability, which is the retransmit of M3, you block that. So you never retransmit this M3 from AP. That's one way you could do. And the way to do that is just set the retransmit counter of M3, the application layer counter, to 0. So what will happen is it will never get retransmitted. And if M4 doesn't come in time, the host AP driver, at least, it's always send deauth after that. So what it will make client is to go start from scratch, right? So that's better than exposure to the attack. So, and this is the initial stage of the connection. So if the client starts from scratch in a legitimate case where there's a legitimate loss of M4 because of noise, it's not going to affect significantly. I mean, probably another 1 second or 1.5 second delay in setting up connection, right?
Okay. So when you click when you click connect and you see the little wheel connecting to the Wi-Fi, it might take a little longer to connect.
Yeah, exactly.
But if there's no man-in-the-middle attack, you might just connect at the end.
Yes. So in this case, the real error is not distinguishable, right, from attack. So if there is a real error, it might take a second longer for you to connect.
So in theory, if there is a man in the middle intercepting the M3, the client will just stay on the loop and never connect, right? If you do.
Yeah, good points. Yeah. So you don't let it connect because there's man in the middle, so you remain protected, right? That's a good thing. Yeah.
And then you can do WIPS containment.
You can do WIPS containment, yes. I mean, if you don't even have a mitigation patch on AP, then, like I said, it requires MAC spoofing AP. And in this case, detection of MAC spoofing is rather simple, because if you have to make it work, this attack reliably, you need to bring this MAC spoofing AP on another channel, because you don't want, the real AP to hear that M4 that is coming from client, right? That the one you are blocking. So you need to have that on another channel. And if you have 2 MAC addresses for the AP operating simultaneously on different channels, that's an easy MAC spoofing detection. I mean, we are not going into other MAC spoofing detection scenarios, but just a side note there is that that's not all about max spoofing. Max spoofing also is used to detect rogue APs which are connected to enterprise network, which spoof, and then they could come on the same channel. They might have very similar RSSI, and those detections are difficult. But this one particular, where because of the channel difference, I think it's pretty easy to detect, and it's also easy to contain because you can do these heuristics that the one that came up later, right? So your authorized AP was operating for a long time on, let's say, channel 36, and this new AP shows up on 40. You can kind of just contain that one on 40 without affecting your legitimate AP. So in this case, detection as well as containment seems pretty robust. And that's what VIPs can do, right? Until you patch everything.
So do you contain the AP or do you contain the clients trying to connect to this man-in-the-middle AP?
Okay, so that what you want to do actually is only contain clients. So when you contain clients, you do using unicast diodes, right? Spoof unicast diodes from the VIP sensors.
Okay, perfect.
Yeah, correct.
Okay. All right. So do you want to talk about the other CVEs, the one attacking the group key handshake?
Yeah. So kind of, if you think of how M3, M4 operated in EPOL, right? M3 was transporting GTK and IGTK, and then M4 was acknowledging that fact from client to AP. So if the group key handshake comes into picture when you just refresh the group keys, on why that happens, the common case that happens is when some client leaves the BSS. So if I'm an AP and some client leaves my BSS, then what I don't want to happen is have that client knowing my group key, because it's not part of my BSS anymore. So the AP, what it would do is refresh this group key and send it to everybody who is still connected. So that's usually when this group key handshake is performed, when some client leaves, but it can also be performed when refreshing the group keys after an hour or so. So that group key handshake, it's two messages, M1 and M2, and they kind of map conceptually, functionally to this M3 and M4 of EPOL, because what they are being used is to transport group keys, which is what M3 and M4 of EPOL was doing. And so the attack operation is similar then, like where you were blocking M4, in this case we'll block M2. Then M1 gets retransmitted from AP and it reinstalls this GTK, IGTK in a client. There's one small caveat there, is that see, this GTK, IGTK also carry the currently running sequence number at the AP. And the reason for that is when a new client joins, right, then the keys are not refreshed, but just existing keys are transported. And the sequence number for them has already progressed because they were already being used before this client came. So the packet number that is currently in use is actually transported in this GTK, IGTK message 1, and that requires some additional job to be done by the man in the middle, like blocking, but like first of all block M2, then when retransmit M1 comes, hold it for some time and then release it. So similar with some differences, but what it's going to do in the end is reinstall GTK, IGTK in the client, and that causes potential for replay of messages that are protected by GTK, IGTK into the client, right? Those are basically 8081, 13080 and 13081, which talk about this handshake process, the two message handshake process that is abused.
So are we only talking about packets being protected by GTK, like, broadcast and multicast traffic?
Yes, for 13080, that's a GTK refresh attack. So only the broadcast multicast packets and like data packets for GTK, right? And then when we are talking about 13081, we are only talking about broadcast multicast management frames transmitted by AP to client.
So what's really the impact of that? Because like, is there like I cannot really see a big impact of, being able to see any broadcast on multicast traffic.
Yeah, we don't use that a lot in our normal kind of mainstream applications today, right? Even if it is like a TCP based application, it's going to filter replace, right, at the higher layer. But what people say is if you have some kind of IoT applications that are using, so you want to kind of send some information to bunch of sensors, right, to change their settings suddenly. So, or if you're using ARPs, but repeating ARPs doesn't look like a big problem, but yeah. So again, I mean, impact of this is pretty limited, I think. But if you have an IoT application that fails on replace, then yes.
Okay, I see what you mean.
Yeah.
So it's more on the client side. If the client doesn't really handle replace really well, you can take advantage of that to perform other attacks.
Yeah. And researcher also pointed out NTP, though it's not direct straightforward, but he has given a reference. I read through that, probably too detailed to cover here, but some internet control messaging that is on UDP cannot handle replace at the top, could be abused. But again, I mean, the exposure is kind of limited again to what I told before. It's about 20 seconds and then or 20 cycles of the two-way handshake, right? So
yeah,
whatever happens during that time.
Okay, so what are the countermeasures against this attack?
Countermeasures similar. So we discuss what you do is obviously the client side fix is very easy to imagine. What you did, you already said that before. So that same function will also block this, because if you kind of use that function anytime you reinstall, the function first check that what I have installed already is it same as what I'm going to install, right? And then if they're identical, don't do it. So that kind of single fix actually fixes all client-side vulnerabilities in this case, all 9 of the 10. So that's straightforward. From the AP side, conceptually, again, same. What is causing problem is it retransmit of M1. So don't let it happen, right? So don't retransmit M1. And then what's going to happen is there's going to be deauth, which is already how the host AP driver behaves, right? If it's retransmit counter for M1 has reached 0, so the client will be deauth. It will go back to the starting point, and here it's a little bit annoying because like if you're distributing keys GTK in the middle of the connection generally, right, to other clients, at least if the new client will get GTK from EPOL, but the other clients are getting it in the middle of connection because they're already connected. So they kind of will go back to starting point. So their connection will break. It's some annoyance, like if you're running a video conferencing session or something, then it might break, right? Because restarting, getting new IP address, setting up connections. So that's nuisance. And if it is a real attack, it's a different story. But if it is a legitimate loss of one of the messages, right, M1 or M2, then breaking those connections might cause nuisance. So it has some nuisance issue, this fix on the AP side. But it's the choice. So, I mean, some vendors might do that. For example, I know what we did was we have given this an option. So, if you can't patch the clients, it's your choice, right? If you enable that option, the mitigation starts. Tomorrow you are convinced that all your clients are patched, then you turn it off, right? So that's one way to do it. Give choice to the network engineer to decide what they want to do, what is their exposure risk appetite, right? Or is the disconnection problem more severe to them, or is avoiding risk more important to them? And then they can decide, right? So it depends on how you want, what is more important to you.
And then you can also do whips containment as well.
Yeah. The operation is same, because somebody has to come as man in the middle to be able to see those group handshakes going, right? And then and again, those group handshakes are encrypted, so the man in the middle cannot see them as group handshake, but you can you can guess them based on sizes of packets, for example, right? So
okay.
And then say that, oh, this must be group handshake going, so I can block this M2. So because you need that man in the middle, again, whips can detect and protect you. And one thing about whips is the deauth we discussed, right, Francois, in the previous section. Yeah. If these guys are using MFP, management frame protection, then the containment of those will be difficult, those rogue APs or the max spoofing APs, because a whip sensor cannot just send spoof deauth and break them, right? Because they are using management frame protection. When you talk about IGTK, for example, if it is IGTK is in the picture, then you have .11W enabled. So containment will be difficult with just deauth, but at least you can detect, correct? And then raise an alert, and then somebody has to. Then whips can also location track, and in this case it's easy because you get different signal strengths, patterns on different channels. It becomes difficult when max spoofing APs are on the same channel to separate their received signal strengths. It's doable, it is done, but in this case it's easier. Like whatever I see on 40, I location track it based on the signal strengths I received on 40, where max spoofing AP is, because my real AP is on 36, so those signals don't mix, right? So you can use whips to get detection on this, definitely. And that's called what we call zero-day protection in security terminology, which means 0 day is when you don't know what an attack is, but are you still protected, right? That's called 0 day. And that's basically means that the day attack is discovered, if I have this running, then, that attack was still not effective against my network. And this terminology is used everywhere in the intrusion detection field, right? 0 day protection. So this is basically a 0 day protection for these.
So different way to protect once again, the best way is to patch the client. If you cannot patch the client, you can do some AP mitigation by not retransmitting M2. And then you can also do some detection with the whips and detect the mine in the middle and raise an alert.
Yeah, raise an alert, location track, and all that stuff. Good stuff. Yeah.
Okay, and then so let's talk about another one, CVE number 13082, which is attacking the 802.11r fast transition handshake, and this is actually the only one impacting the AP itself.
Yeah, it's one impacting AP, and this one is really interesting because this one doesn't require man in the middle, so it's very easy to launch. You can be just a sniffer, like a Wireshark sniffer, and then replaying some packets selectively. So it's much simpler to launch, and the time duration and the number of packets impacted here can be significantly large, like hundreds, thousands, like that. Right? Or the time duration for exposure can be minutes to hours. So I think this is really the very most severe among all of them. And then this one abuses four-way handshake that happens at the time of what we call fast transition. Fast transition means when a client is moving from AP to AP, what the fast transition protocol 11R does is it doesn't require the client to go through what we call EAP, right? EAP is the phase when you are authenticating to each other and then generating the master key, because it takes long time to do that, especially if you're going back to the radius server. So what it does, 11R, is transfers this PMK. Actually, there are two PMK generated in this case, R0, R1. So the R1 is for distribution to the neighbors. So it distributes this PMK to the neighbors already, neighboring APs, right? And how to distribute that is outside the scope of the standard, but 11R. But when the client goes there, the PMK is ready, and then it basically runs the same EPOL four-way handshake. Only difference is that it's piggybacked on authentication and association messaging too for speed purposes, but it's still four-way handshake. A small difference why this happens on AP side is that it's reversed, meaning in normal EPOL four-way handshake, that's initiated by AP by sending M1 to the client. In this case, the M1 equivalent of M1 goes from client to AP during an authentication request frame. Okay, so it's same one, but it's reversed, and because of that, if you block the message M3, then it's not M3. If so, it's reversed. So that's why it's on AP. That's the intuition behind that. And the way it works is that the last two of these authentication association or reassociation request going from client to AP and reassociation response going from AP to client, that would be equivalent of M3, M4. So in this case, what you do is don't block anything, but you just replay this reassociation request at a later point in time. And then it reinstalls the keys. And the reason a simple replay works, the real difference is that we are not going in details now, but the M3, M4 transactions have application layer replay protection in them, whereas reassoc request response do not. I mean, this is an example of how applications may be resistant to replay, may not be resistant to replay. So reassoc can be just replayed and keys can be installed anytime, right? So you like the first handover has happened. The client is communicating for 5 minutes, has sent 1,000 packets, and now you can replay that reassociation request. And then you get all those packet numbers, 1,000 packet numbers repeated. So that's really 11R vulnerability, which is, I think, one of the most severe ones among these all, because the reason I said long times, large number of packets, no man in the middle required.
So when you talk about the key and reinstallation here, you're talking about the key being reinstalled at the AP side, right?
Yeah, on the AP side, and this is PTK, the pairwise key, right? Okay. That's reinstalled.
And this is only if you use 11R.
Yeah, if you only use 11R, because that whole process of reassociation request response happens only when you use 11R. If you are not using 11R, when you change an access point, you are going to EPOL four-way, right? Handshake. I mean, from the beginning. So like EAP and then EPOL four-way. So it happens only with 11R.
So the way to fix this one would be to patch the AP, right? So the AP doesn't reinstall the key.
Yeah, same logic that if you have it already installed, when there is a need to reinstall, just compare. So it's pretty easy fix. So good thing about all these fronts is that the fixes are not difficult, right?
Yeah. And if you have, I'm thinking about people having home routers, Soho routers that don't support 11R. So in this case, they don't really need to patch the router.
Yeah, you are right. And even distributed deployments, right? Single AP retail, they don't have 11R. So those are difficult to patch sometimes. Enterprises, carpeted enterprises probably use 11R. These days, there's a increasing number of deployments using it. There were issues with 11R earlier, so people did not use it. But I have seen it increasing again, the adoption. So there is where, you either turn off 11R or you get this simple patch. I mean, it's not a difficult patch. Yeah.
If you have enterprise grade APs, the patch is already available.
Yeah,
pretty much by every vendor by now. So
correct.
Okay. All right. And to finish, we want to talk about two CVEs that are, we haven't heard much about them. It's CVEs 13084 and 13086, and they're related to attacking DLS and TDLS. Do you want to explain that a little bit?
Yeah. So these modes, right? What they do is the clients first connect to access point, and then what the clients decide to do is, hey, I mean, we don't want to go through access point every time. And there are two reasons for that. One could be you want to run high bandwidth multimedia, right, between two, like TV and a display, right, or a projector and a TV, right? That traffic doesn't need to flow to access point. Then they go first. They have to go through access point. They have to connect to access point, and then through access point, they decide to talk directly. So it's different from what we call ad hoc mode of Wi-Fi, because you first go through AP, and through AP you negotiate this session, peer-to-peer session, and then once it is negotiated, you directly transfer traffic to other client, right? Another important application for that is in IoT, because think about large number of IoT sensors away from the AP, low power IoT sensors, and if they have to talk to each other, which are close to one another, it's just that the AP is far away from them. Then every time they don't have to spend a lot of energy going to the AP, because they can just send a small packet locally, right? So these two applications were envisaged when these modes were designed. And DLS, TDLS both kind of achieve the same purpose. Only difference is DLS has more involvement from the AP to build this initial session, but TDLS actually is completely transparent to AP, so it's tunnel. So DLS I haven't seen a lot, never kind of took off. TDLS, at least it's supported in drivers, right? And so these when the clients, you can imagine, negotiate the key for traffic that directly goes between them, that's where EPOL four-way handshake like transactions happen between the client going through the AP. And that's when you can attack in the same manner that you did for EPOL four-way and have the keys reinstalled in them for peer-to-peer sessions, right? So the mechanics is similar. It's just that the specific mode is when that is used. So they assign different CVEs for them. And I haven't seen DLS, to be very frank, anywhere. But TDLS, at least the implementation is there in the drivers that are used today, like host AP. Maybe become important in IoT, who knows? So again, and the same fix would work, it's just that it's yet another key called peer key. So if you should do this fix for every key you reinstall, then it should take care of everything, right?
Okay.
Yeah.
All right. So perfect. So to conclude this very technical episode, thank you, Hemant. It was really, really good.
Yeah, thanks for having me.
No problem. Do you have any do you have anything to say to all the engineers out there trying to deal with the KRACK at their workplace or with their customers? Like, maybe, I don't know, give them some advice on how to deal with the situation. The impact. We talked a lot about the countermeasures and the solutions.
Yeah. So, I mean, I always follow this thing, right? If you come from the security side of the house, then you would say that, okay, so vulnerability discovery happens every day. So, like, to give an example, every Monday, like for the cloud side of it, there's Linux, there is Apache web servers, there are databases. Every morning I have a meeting with my security team for the cloud side. We go through all the vulnerabilities that were advertised last week, and you always get bunch of them, right? High, medium, low. So first thing we say is there a patch available, right? Can we patch it? Now, if you can patch it, it's much easier, because you practically cannot analyze each one of them and see, what the impact is, right? Number one. And number two, a lot of these compliance contracts or the contracts you have with customers, they require you to patch anyway. Like if it is high, they want you to patch in 30 days, moderate, 90 days, right? Things like that. So you have to patch anyway, otherwise you fail the security audits. So one advice I have is, okay, so vulnerability is out. If the patch is available from your vendor, and if you can do it, then just do it, right? And then you can analyze, like we are analyzing what the impact is. But if the patch fixes it, that's your first line of attack. If you have difficulty in patching, maybe because the patch is not available, or you have a deployment that just cannot even go down for 2 minutes, right? It's very critical stage. That's the time you got to come in and analyze what the impact is. And in this case, I would say it is okay to wait at least for those EPOL and group key, right? Vulnerabilities. They are not extremely severe or not very severe. Even the US CERT has given them moderate, right? The R1 is a little bit more severe, but again, I mean, given the fact that you need local vicinity, all that considered, you have to analyze your own risk appetite and then, or just disable 11R, right, until you patch. So that's a two-step process. If you can patch, just do it, and if you cannot, then analyze, and at least for 11R, disable 11R. Okay, that's your immediate solution until you get patching. And that's really my advice. And we are fortunate here that the few good things coming out of this you have to analyze. I mean, the researchers pounded this protocol so much and they got only this out of it. So it's good that it proven the strength of the protocol one more time. And for the GCMP, we already know where the impact was large. We now already are fixing it. So by the time our YGIG comes, this vulnerability won't be there. So there's several good things that have come out of it as well, right? From the community standpoint, that the security of WPA2 standpoint. So that's really the gist of it. I mean, it's very interesting, clever, increases our security of WPA2 definitely, and then there are solutions available. So overall, it was interesting episode, but did not cause much harm to our Wi-Fi security at least.
So do you think WPA2 will still be used for the years to come, or do you think they will be working on a new standard, WPA3 or something?
I don't see a need for that, because GCMP, CCMP are all currently approved NIST protocols, right? FIPS protocols. So the encryption is solid, four-way handshake, everything is proven. If there are issues like implementation issues, like issues with the random number generations, right? If there's an issue with your random number generator is several times an issue in implementation, because this, in four-way handshake, you send something called nonce, not AES nonce, another nonce, which is supposed to be a random number. Now, if your implementation is such that it generates predictable random numbers in the beginning, because how the random number generator is initialized, right? It doesn't have enough entropy. Then these protocols are not secure, because they are based on assumption that when cryptographic algorithm says a random number, it has to be really random, right? It cannot be predictable when you boot up and things like that. So the implementation issues can still be issues going forward, especially in IoT space, because what IoT guys will do is, because they have to fit that software on that 1 KB memory, they will cut some functions, right? And not necessarily analyze what they're removing. Maybe they remove the function that the check on whether random number generation has enough entropy, right? And those kind of issues, if they arise, then obviously we'll see more of this. But other than that, all this is very standard approved kind of mainstream cryptography and handshake that are used here. So it's pretty secure, I think.
All right, Hemant. So we could go on and on for hours, but we have to end this episode. Just to finish, you did a very good video series explaining the different crack attacks with Vivek Ramachandran. So we will link all of these videos in the show notes. I think you can also find them on the Mojo Networks blog. I also did a blog on my article. It's called Fully Understand Crack in 2 hours, and it's basically watching your videos and reading the paper of the researcher. And also there's the video on the four-way handshake right at the beginning by Mark Burton to understand it. But anyway, if you want to see, have a visual of everything we talked about today, you can watch Hemant's video. They're really good. And you created slides to explain the different packet exchange and which packet is blocked and which packet is resent and everything. So it's a very good visual for to complement this podcast. And before we close, Hemant, do you have where can people find you online?
Yeah, so I'm already visible, I guess, to people in community. C Hemant C is my Twitter, so send me, messages there, whatever. And then you can also reach me at my first name dot last name, Hemant.Chaskar at mojonetworks.com. That's my email. So you can reach me anytime if you need any more information or your interesting insight to share that I haven't appreciated yet. I would be looking forward to that.
Well, thank you very much for coming on the show today. It was really good. We get a lot of information. I'm sure the audience will appreciate all the technical details. And if you like the episode, feel free to leave us a review on iTunes and tell your friends about the show. Thank you very much, and see you next week.
Okay, thank you, Francois. Thank you, Ravel.